Hey there, my name is Lester Martin, and I want to present a video of a presentation I'm putting together. It's as titled, Building Java Streaming Apps, and with a focus on Apache Storm. Before I get going, of course, just a little quick introduction about myself. I am currently a trainer and consultant at a major Hadoop distribution vendor. Maybe the color coding helps you here. There's my personal email and kind of a portal page to things on the web that might be of interest to you. Feel free to reach out to me if that's the case. But what I'll talk about today is really, again, a quick introduction, some quick demonstrations of Apache Storm. So we're looking for folks that are relatively new to Storm or maybe have done a little bit of experimenting. This is not an advanced conversation. It's a much more introductory. So as it says there, we'll just rattle through what Storm is. We'll talk about the conceptual model. What are the major stereotypes? What are the pieces of code we're going to write, and so on. We'll transition into the compile time, the development time activities. So we'll actually build out a workflow with all the different component types, and then we'll do a quick demonstration of that. We'll talk about what you need to do to build, and then we'll build them. Then we'll transition into, okay, now that we built something, how do we deploy it? How do we submit it? How do we monitor it? How do we see it running? So we'll kick off into a demonstration. We'll follow that up with a demonstration. And then lastly, just present a few other features, integration points, etc. And finish with another, a little bit more end-to-end demonstration with a few technologies. As I mentioned there, Kafka into Storm, and ultimately back to HBase, and actually back to Kafka as well. So I think a quick introduction here. So what is Storm? Storm is, well, it's a number of things. For sure, it's streaming. It's event level processing. I've got a slide in a minute just to remind us about the Lambda architecture, but it's definitely a key point of a large, multifaceted, multi-technology software stack. Storm is definitely fast. So we're talking about, this is an old metric here based on several years ago, but we're talking about easily 1 million events per second per node, per machine. So imagine a cluster with 10 machines, 20 machines, and so on and so forth. Could we do more and more? Or imagine some machines that are even bigger than that were used in that benchmark out there. Scalable, we're talking about running lots and lots of machines, lots and lots of workflows. That's just at heart fast and scalable. Performance and scalability, of course. Anything that's cluster technology, many components, we're expecting completely. We're expecting the system to deal with failures and keep on moving. So we're looking for resiliency and fault tolerance, high availability, etc. And then lastly, pretty much something that separates some of the less mature frameworks is this notion around reliability of events flowing into the system, and then the kind of holy grail or unicorn we're all looking for in stream processing, which is this notion of exactly once processing. We'll talk about some of those semantics as well. If you put it all together in a big picture, and this is somewhat a liberal view of the Lambda architecture, where we think about things like batch layers. Hadoop is definitely a good example of something like that. We bring lots of data in, we can run lots of analytics against that, crunch, come up with great numbers, great insight, etc. But then sometimes we do also need, either for some of that same data, possibly other data feeds, we need some opportunity to look at that data near real-time type activities. As soon as it's raised, make some actionable event on that. Maybe it's some healthcare data. Maybe it's just a smart meter system and a utility grid of some sort, and you want to be aware and look at things. Could be just as much, could be a watching the website activity on your popular website and looking for fraud detection, those kinds of things. And as you see here, there's a lot of give and take left and right here, because these are somewhat of a incestuous model. They help each other out. The batch frameworks end up producing insights that can be leveraged at event by event to say, hey, is this good? Is this bad? The more data we get, the better answers we have. So we're looking at constantly updating either configuration, or as it suggests, there may be full true models, software models to help us predict good answers on the fly. And then this information that's coming in coming in from the speed layer will make it back into the batch layer. And then toward the bottom, what you see is that notion of a serving layer. There are going to be times when once that information is calculated, valued, created, maybe pushing, egesting that back out of these systems into something a little bit more performance oriented around quick reads, user interface, etc. So an application tier, a database tier, and it could be some of these technologies. Could be the NoSQL systems, Hive, as well as other popular data persistence technologies, and even just homegrown applications. So we'll continue on the conversation and really just dive in and try to understand the conceptual model, the object stereotypes, etc. that exist inside of Storm. At heart, Storm is an event-level processing engine. So we're doing streams of events. And events, in Storm's vernacular, we use the phrase tuple. Definitely a term we've all know and love from our database backgrounds. Usually a row of data, something like that, very well organized, with data types, etc. And really no difference here. A tuple is the event that will flow through the Storm engine and work through our workflow. It's an immutable set of values, as it kind of suggests there. These are values. It's not necessarily an XML stream or JSON stream that has the data definition, the data column names, those kinds of things. We will define those somewhere differently, and we'll just have the values, again, mainly to focus on performance and scalability, and no need to carry forward that information over and over. Those values, those tuples, are going to be put together in what we call a stream. Probably pretty straightforward concept. And I think the phrase up there, core abstraction of Storm, is probably fair to call it that, because we don't really create a stream ourselves. We declare component types. They raise tuples or they consume tuples. And the connection of those is, in essence, our abstraction of the stream. Obviously, Storm, the running framework, is a bit of an orchestrator, and he'll make all these things come together for us, but we don't really program a stream, per se. We emit tuples as we go along. And obviously, we're talking about running this forever, so it's an unbounded sequence of tuples. How fast they come? Well, it's all about the data that we're consuming and bringing in. That's a good transition to the next major component, and this one actually is a component that we will either build or we will leverage. Maybe take one of the existing spouts that are out there. So these are component types that latch on to some kind of data downstream. Could be a message queue, could be a database, could be a socket listening application, could be the delivery of data in a directory. It could be lots of things, but this is our software component type where we collect those events and then formally raise them as tuples. Complexity in Storm allows for lots of minis. Well, we'll keep it simple in today's conversation and kind of suggest maybe that a spout only can raise one kind of event. It could raise multiple kinds. Same thing with these other component types. You'll find out they could consume as well as raise multiple types. We'll just keep it relatively straightforward. So we're at a piece of software that listens to things like a message queue. So message queues are not part of Storm, but they definitely are good event sourcing things that spouts can connect to and consume and raise them up and then pass them into the workflow system. And in fact, that's just probably one of the better ones out there. Other things we can do for sure. And the one we'll probably focus on today in the demonstration a little later is Apache Kafka as the message queue. So we went from Spout, tuples, spouts, and then we have a concept called a bolt, a software component called a bolt. And the bolts really are the majority of our workflows. They are the things, the somewhat isolated, somewhat loosely coupled system event activities that do something, as we suggest here. I'll talk about some of the things they might do in the next screen. They might often, maybe toward the end of a workflow, once work is decided upon and there's an event that we want to hang on to, maybe we write to something like an HBase, a Mongo, or some other database. It could be any kind of persistent store. It doesn't have to be one of those. It could be write to a socket itself, connect to some other listening application, write to a service call, etc. We can obviously we can pretty much do anything. These are software components that we're going to write to a well-known interface. So an example could be, we could read some data, which could be configuration information. More likely it's probably augmenting type information. Now that I found something of interest, maybe I go fetch a little more. Maybe I realize this customer might be doing something very positive or very negative. Maybe I go fetch their deeper history so I can make a more educated decision about what I might want to do next. And I probably could have started with this, but to be honest, this is probably what bolts are doing the most. They're figuring out things. Maybe they're keeping track of some role in history. Maybe they're looking for something that says this is a bad event, this is a very good event. So any kind of arbitrary computation. We're going to see a little later in the demonstration that we'll write this code. We can do just about anything we want because we're in our code base, and we'll do that today in Java. And bolts themselves could raise tuples themselves. It could create a stream of data for someone else to consume. And in fact, we will see that to wire things together, we'll see usually as something like as simple as a single spout raising tuples through a stream, and then more and more bolts listening to that, and then those bolts themselves may keep the data stream going by passing either the same information, augmented information, completely different information, maybe just a subset of that information. Could be a variety of things, but this is how we leave data, emit data outside of our bolt for someone else to consume. And as I was suggesting, you'll put all this together into the kind of the final, what is a workflow, and we refer to that as a topology. And topologies are running DAG, or directed acyclic graph. The events in the order they have to execute to get the job done of spouts and bolts. Now this one's showing a mildly complicated one by the fact that we have two different kinds of spouts here is what we're suggesting here. For the most part in the demos today, I will keep it very straightforward, a single spout raising something in. So maybe like this spout here raising an event, maybe a bolt that cares, maybe this guy, and then maybe he also sends something downstream. You could jazz it up and do a variety of things. Ultimately this is your data flow representation. This is your streaming as opposed to batch. It's your streaming computation. And what makes, I think, Storm somewhat unique is its inherent ability to help you parallelize different elements within this topology. So these are different types of bolts and spouts here, but when this is a running workflow in the system, a running topology, we can in fact turn levers up and down about the number of instances of each one of these components to keep up with traffic. Meaning, if this middle bolt right here in the very center was slowing this topology down, could we add another instance? Could we add 3 more instances and allow the system to catch up and continue on? So slow moving components, slow heavy processing components, we might need more than one so we can share the load and individually parallelize. Now the next slide is going to be a little scary at first glance, but it's not as, a friend of mine said once, it looks bad, but it's not as bad as it looks. So I'll take that and run with it and try to explain this slide, and then the next slide maybe give you a little more details. So because, I guess explain first, what are we trying to suggest? We're trying to suggest we have a logical topology that's pretty straightforward. A single spout A, and spout A is emitting tuples, and we configure it up in our topology 2 other bolts, bolt A and bolt C, that both independently care about the events that are raised out of spout A for whatever reason. Maybe C is a emailer, maybe he's an alerter, maybe A has done something completely different. So 2 different computation bolts that need to do something different. So we wired them up. And then we also said, look, bolt A, when he finishes, he has the potential to raise other data, again, the same or different, modified, replace, whatever data or subset of data, down to another bolt B to consume. And so there we go. 1 bolt, 1 spout, 3 bolts. What we're showing on the right is what I was suggesting, that we can individually parallelize these different components. And if you look really fast, you might get what I'm suggesting, which is, hey, what if we had 2 instances of every one of these components, except for bolt C. Maybe bolt C runs pretty fast and lean, and we don't need more than 1. So what we're trying to show is spout A has 2, and don't get too worried about these nesting here. There are some rhyme or reason, but it's from a bigger conversation. Let's just say this orange square is the running instance of spout A, and we just happen to have another running instance of Spout A. They're just making the point that maybe this could be very distributed across a whole bunch of machines. In fact, we need 7 instances, and we're doing a completely spread out and distributed running topology. So every single instance, every single component is running on a separate machine. And that's not unrealistic in Storm. Storm likes to go wide, take advantage of spreading the workload, keeping performance up, and it does imply there is serialization going on behind the scenes to get things around. So 2 things I want to get out of this. One, we can individually instantiate additional. We can scale up or scale down. We can elastically change the number of instances of a particular component at runtime. So we're just showing you 2, 2, 2, and 1, but we can change that as we go along. We notice via monitoring or any other mechanism that we need more or less instances. So that's point 1. And then point 2 says, well, if that's true, then what do we do? How does instance 1 of Spout A, knowing that he has to send his data to A and B, how does it get there? Or how does Storm do that for us? We don't write the code for this. We explain how we'd like it to be grouped, how we'd like to handle these streams. It's called streams grouping. So it's very easy to determine how we get to bolt C, right? Machine A, node here, component here and component here, the Spout components, they both individually know, hey, I got to send down here. But it's about this guy. What do we do here? And if you think about it, if we think about scaling up, scaling down, and we're thinking about scalability, probably what we're imagining is, couldn't we just round robin? Sure we can. We'll show you in the next screen. That is a very popular model. So as every event raises out of here, from Spout A going to Bolt A, this guy sends 1 here, and then he sends 1 here. 1 here and 1 here. That's a very popular way to do it. Same thing, B goes here and here, here and here. And the same thing through here. So we call that streams grouping. And we do have a few options as we look at that, and I'll show you the primary ones here on this quick table. First and foremost, the well-worn, well-utilized, makes a whole lot of sense to all of us, is a shuffle grouping called a stream groupings called shuffling, which randomly, I'll go ahead and say round robin amongst those events. Yeah, I think the key word about random is evenly distributing load to downstream. Net, we visualize that as a pure round robin. The second one is another very popular one. Is called fields grouping. And this is where we would like to say, hey, I want to make sure, based on a particular value in the tuple, 1 or more values, I want to make sure that every one of those go to a particular bolt. So if we're keeping track of some kind of running average of something by maybe a zip code or a data center or some in those tuple, there's a value in there that says, hey, I want to hash based on that. We could do a fields grouping, and I'm gonna go backwards, so that every event that comes out of the Spout for a given field, we make sure it goes here. So again, maybe we're doing some kind of averages by zip code. So I want all the 90210 events to go here or here, doesn't matter, but I want them to all go to the same place. Maybe the 3004s all in on machine D. So it's fields grouping as a way to basically let the system do some basic hashing algorithm amongst how many there are, how many instances downstream they are, and then route things appropriately. Very powerful, very useful. We need to have contextual differences, and we want to make sure across those different instances that we got to have for scalability, we can still have some kind of correct answer. So very, very useful. We'll use that in an example demo here in a few moments. And then probably to me, while there's 6 or 7 of these things out here, probably another real common one is this notion of sending to them to all. And this would be good for, go back again, this would be good for every event coming out here, send it to here and here, right? Always send it to both. I would say as the main driver, the main spout in a particular topology, all distribution probably makes no sense. We get no value on scalability by having more and more downstream. If we have to send it, instead of 2, I have 12, so I have to send it not to 2 places, I have to send it to 12 places. In fact, probably a law of diminishing returns that's going to bite us in the rear pretty quick. But it would be good if we had a topology that had more than one spout. And those spouts could, maybe 2 examples. One could be maybe we have a spout configured to some weather data. Maybe our streaming topology cares a little bit about getting all these events that are thousands, hundreds of thousands, tens of millions, or whatever events a second. But every once in a while, weather information comes in, and we want to take advantage of that and make decisions based on good and bad weather, etc. So maybe we let that go to everywhere. And just as much a concept that we sometimes refer to as control streams. We mentioned earlier when we talked about the Lambda architecture that maybe we want to send down from the batch layer, we come up with some new values, some new models, some new configuration. How do we inject that back in there? Well, we're writing code and we can do all kinds of cool things, but might as well use the dog food model that says, hey, wire up control streams so when system information has come along, I can share it to all the running components. So that's a popular one. There are others, including the notion of creating your own custom logic that determines how do I take advantage of those downstream activities. So that takes us to a little deeper conversation now that we have a good understanding of the different stereotypes, the different component types that we're going to build, and we'll talk about the development time activities that we would typically do in our IDE, and again to focus on Java. So first and foremost, we're going to talk about spouts, but we're going to show spouts, bolts, and topology examples of how to make something come together. So as you probably would expect, there's some kind of spout interface out there. Of that spout interface, there are some existing abstract classes. So this is an example of extending one of those, a base-rich spout. And just to give you a little indication of what we're going to do with this, we're going to build a custom spout that just produces random sentences. So we'll get to that in a second. There's housekeeping methods. There's an open method. There's a corresponding closed method. Those are our opportunities outside of the normal constructor, deconstructor type object level things for us to be told by the framework, hey, get yourself ready. Maybe this is something we do connect to a database or something, or a downstream system. But more importantly, it's about coding the workhorse of a spout. And the workhorse method of the spout is, as you see here toward the bottom here, about halfway down, the next tuple. This is the method that Storm's going to call over and over and over again when the overall orchestration framework says, I'm ready for another event, give me another event. And this is the one that we're talking about in those hundreds of thousands, millions of events per second type activities. This is clearly, it's got some homegrown logic to kind of slow it down for us to maybe debug and try to understand visually what's going on. But what is this thing doing? It's a random sentence spout, so it is randomly emitting a sentence from a handful of well-defined sentences as you see there. So that's really what we're talking about. This would be the thing that listens to your message queue or something like that. And something to consider, I'll come back to that in 1 second. Another workhorse method, or another intended method, is this declare output fields. So we need to, because the tuple that gets raised is absence of any details about, it's got 3 values or 10 values or 1 value. It doesn't carry forward one of those field names and that kind of stuff. Here's our chance when asked very early in the framework, hey, what are we going to raise up? I'm going to raise up sentences, a 1 tuple called this made up of sentences. If I was raising up maybe an employee record, it might be employee ID, first name, last name, date of hire, those kinds of things. In that situation, I've got 4 fields, so I might call that a 4 tuple. So declare output fields tells the system what we're going to raise. The next tuple method is our opportunity to raise another one of those events. And then there are other methods. You see this ACK and fail. I'll come back to those later when we talk about reliable operations. This is our opportunity to kind of participate. Before I move on off of Spout code, let me say this. While I'm showing this first demo is going to actually build out a Spout, more than likely we're going to take take advantage of the fact that there are a number of spouts already created that are configured to different kinds of data systems. Eventually in the labs, the demos here, we're going to transition to use Kafka. So we're going to use a existing bundled with Storm, Kafka spout, and not have to create one of those, just instantiate one, give it some configuration and move on. So spout code, next tuple. The bolt code is, similarly, there's an iBolt type interface out there. There's some subtypes of that, a base-rich bolt, a basic bolt. We're going to talk, not get too focused on the couple different abstract classes and why they're subtly different. It's more than we have time for today. But this is going to show you just an example by looking at the name, the exclamation bolt. And if you just kind of dial in right in the center, there's a method called execute. This is corresponding to its sister element's next tuple. This is your opportunity to work on a tuple. As you can see, the method signature has a tuple. So we're looking for Storm to be the overall orchestrator between that spout and that bolt by the fact that we said this bolt listens to that spout. He's going to coordinate all this together. He's going to pull a message. He's going to send us a message to invoke and to process, and then based on what we do, continue on or maybe halt that processing. So execute is our workhorse. We do our mojo. We have a similar declare output fields just like the other one because we may choose to in bolts. We don't have to, but we could also raise data. So in our case, we received a sentence, and we're saying we raise a word, but if you really look at this hard, we're actually raising, another sentence, exclaimed sentence with intensity. But fair enough, we can call it whatever we want to. And if you looked really hard, you saw that all we did is had tacked on a few exclamation points at the end. And that was the end of our logic. Nothing too magical there. And if you looked really hard and you thought about execute versus next tuple, you might think maybe it wasn't the same person that built these. I would look at the housekeeping methods of prepare and clean up. And they kind of suggest that there's maybe a different person doing one versus the other. That's okay. Nothing to really wrap your head around, get too upset about. And then lastly, we want to put it all together. So we need something to build that topology. We already talked about building a spout. We talked about building a bolt. And here's an example of the fact that today in Storm, we don't really have a visual builder. We write things out there. Some other ways, I'll mention it later, but the kind of tried and tested way is to build in Java code, configuring up a workflow, a topology. So toward the bottom, maybe we, depending on our team and how many people are involved, we'll come up with just enough documentation. Not more than we need, but enough. Just enough documentation. And maybe our case, we came up with this Lester modeling language or Storm model, SML, Storm modeling language of sorts that we put on a wiki or wherever we do documentation. And we just kind of took this notion of, hey, when we talk about a bolt or a spout, let's talk about what class we're using at the bottom here, and maybe at the top, maybe what we'll call it, what we'll name it in our topology, and then who is being connected up, who's listening to who. And then since we have options about how things get distributed, when we have parallelism, let's go ahead and in our little modeling language, let's declare what kind of stream grouping we're going to use. So we're going to build this very simple, straightforward, words go to exclaim one goes to exclaim two kind of topology. What can we do? We build us a Java main. We kind of get a handle to a topology builder instantiation. We'll call it builder. And then just like it says, as you see here from these three methods, we set spouts or set bolts into that builder. So we just kind of work left to right. And it could be very crow's nest. It could have lots of branches and that kind of stuff. A very simple one here. And we get to declare what we'll call these. These will show up in the GUI that we'll see a little bit of a running topology. So we'll call it words. What is it? It's a test word spout. Okay, right. We want a bolt. We'll call this one exclaim one, and it's of this type. Great. And then as I don't know if I made it clear, but what we do in topologies, it may seem like initially that the spout should say, where am I sending my information? But truthfully, the spout's much more the producer. And in this case, the receiver is the consumer. So the consumers, there might be more than one, and they ebb and flow and change. So we're looking for the consumers to kind of wire backwards. So as we declare our bolt exclaim one of this type, we're going to say, hey, look, I care about events that came from tuples. I care about the stream coming from words. So and then this is that shuffle grouping. This is that shuffle fields, all those other kind of stream groupings that I mentioned earlier. We have options. Again, we'll keep it simple. If there's more than one exclaim one instance, then round robin, because we want to do that. And then we did the same thing. We added another. It just happens to be, this is not a real example here. Another example that we'll just use the same class, an exclamation bolt. We'll just call it exclaim two, and same thing. Let's wire it backwards. I'm listening to things from where? Exclaim one. What's exclaim one? The previous bolt. So we're just wiring them up backwards. and we're again using that round robin. Once we get all of our spouts and bolts and all the wiring all configured up, we really just need to use a submitter class to submit that topology off to the running cluster, the running storm cluster that we'll just explain a little bit when we're ready to deploy our code. So of course, why don't we take a transition, get out of these silly PowerPoint slides, and get ourselves over into an IDE. Okay, I jazzed up the slide just a little bit, probably flashed, and there's a little bit of a visualization there in the bottom right corner. What we're going to do is do a demonstration building a word count topology. So we're going to build a spout, much like what we see in a sentence generator. Example ABC, ABC, down the bottom. We'll wire that up to send those sentences to a splitter bolt. He will break tokenize those sentences apart to individual words, implemented by these just little letters. Assume that was now is the time for all good men type sentences, and then we'll route those to a word counting bolt, which won't keep track of just onesie twosies. It'll keep a running total of those words and the counts, the running total counts to that as well. So let's get out of PowerPoint like I promised, and probably go to, before we show that, just make sure everyone knows how to find the Storm website. Simply storm.apache.org, as you see on my browser here, high-level information that we've kind of covered about what is Storm all about. We're going to specifically, in my example at least, use version 1.10. So, you find the version that aligns to you. Why? Yeah, you can learn more about the concepts and everything we just did, but just as much, a quick link to the Java doc as well. So I'll leave that up should we need it. And we're going to do a piece of code that I put in a GitHub project out there. I'll put this back up toward the end of the session as well, but this is the location. Just remember Lester Martin, or just pause this YouTube video and go grab this, GitHub Lester Martin. I'll probably put it in the comment section as well. So I'll go ahead and minimize that. And that site should look like, here we go. So Lester Martin streaming exploration. The one we're going to work on first is, I'll just jump in the solutions. I got a kind of a stub here that I'm going to use and build it out together, but the end solution is just this simple word count. Now this is emulated off the Storm project, has a number of examples, including Storm, including word count, so I want to emulate that. So ultimately, what are we going to do? We're going to build a couple classes here, a few classes here for the spout, a couple bolts, and a topology. As we said, we'll have a sentence generator. We'll have a bolt that takes those sentences, tokenizes them, and then another bolt that does the individual word counting. So that's all available to us. So I went ahead and pulled that project down locally, and I loaded it up into my IDE. And here we are. We're off and running. And as I mentioned, I've grabbed just the one called project, not the solution, so you can implement it. And I've given you a start. I've given us a view of a sentence spout already created, and jacked my font up really big to make it almost useless to me. And I want to go do one quick thing, and in the background kick off a Maven build, make sure this thing is going to run to completion. See if there's a target directory now. Yep, it is. Make that a little bigger so we can see that. And hopefully, yep, build success. And what you're going to see is we're building, while that was a very simple class, we're not even done with it. There's a real small jar file, but you'll find out in the next demonstration, after we build this, we'll deploy it. We're going to use that kind of fat jar, uber jar model, so we're bundling in there a lot of additional things, classes and jars that we need, etc. All right, so let's build this thing as promised. So we have a random sentence spout already out there, and it's already implemented our next tuple. In fact, like the example we saw earlier, it was asleep. I'm slowing it down to about 3 seconds to give us a chance to kind of see it, and I put the sentences a little higher up, so nothing but a little string array. Those same sentences you saw earlier. So the open method has some of the housekeeping stuff. They're really just some boilerplate stormisms here. And the next tuple is actually fully implemented. So we're just randomly getting one of those sentence, the strings out of the array above, and then we're emitting that as that string that we raise up as through this class called a values, a storm class. The only thing I left us to do on this guy is actually implement the declare output fields. I promise the bolts will do them from scratch. So we're going to use something like the output fields declare. We'll do a declare, and we want to declare fields. So we're going to do a new fields, FILDS. That's the Apache storm tuple, yep. And then the fields we're going to raise is actually a thing called a sentence. So this is what we talked about earlier. Yep, there we go. So that makes us a complete and viable spout, random sentence spout. What we want to do now is create that bolt. We talked about we need 2 bolts. So let's create a Java class. We're going to call it a splitter bolt because that's really kind of what it does. And the splitter bolt, he's going to extend a base rich bolt. Sure enough. What am I missing here? Oh, yep, there we go. So let's let it do the implement methods that we really need. Prepare, execute, declare, sure. All right, so we got some methods out there. For us, we really don't have to do anything in the prepare. So we go ahead and let me pause up. I need 1 second. Hold on here. Yeah, I kind of remember what I did. I was confused for a second, so I paused you. So let's go back, and actually I wanted to implement the basic bolt. There we go. And that one has a one less method. I was trying to wonder why we need to do a repair. We're going to keep it as simple as we can and move forward. All right, so a couple things. Let's go ahead and, because I think it's best practice to say what we're going to raise up. So this guy's going to take sentences and he's going to raise words. So let's say we'll declare a set of new fields. We're going to raise a fields object, and that fields object, what fields will we have? We'll just actually have only one. So we're going to take a one tuple that's made up of a sentence, and for that sentence we're going to raise many different tuples of type word to kind of keep it simple. So what do we need to do? We need to grab the the sentence from the tuple. So let's say tuple dot get string by field, and the string name was sentence. So there we go. We got our string sentence. From here, you can do whatever kind of logic that you really wanted to do. And I guess I could have wrapped that a little bit. I can say something like, let's just make a bunch of words. Words equals sentence, string utils dot split. Let's split the sentence. I think the default constructor on that will work for us. Sentence, was it not like split? Split tuple, sentence between, that is a sentence. I cannot reply to string. Well, shooby dooby. What did I do wrong here? I think I imported the wrong string utils. Let's try it again. Mouse over this guy. We want the this guy, the shade comments. There we go. That took care of them. All right, so what did we get? We got from the tuple, we ripped out the sentence. You could put all this in one line here. We'll split the sentence, the default token of the space. We have a bunch of words, and then we build a little for loop. So we'll say string word from words. What will we do with that? Well, I guess just to make it ugly for us, we're going to do the old low-tech what's going on. So I'll put a couple lines in here. I guess we're going to say splitter forward equals plus the word, and then we'll do some kind of cleanup here, plus /n/n. We'll just put a little space here. So we're just putting ourselves a little message that'll help us, because we're going to run this in the cluster. We want to see some details. But really what we need to do is we need to emit out that string. We need to emit a new values. Please tell me I got this right. And it's made up of the word itself. Let's see if I can get that going. So, yep, tuple. All right, so I think what I've created for us real quickly is just a quick little executor here, a little bolt that again takes from the tuple. It rips out the known thing, the sentence, tokenizes that into a bunch of words. For all of those words, we want to raise them up. We want to emit them down a stream. So we got a tuple per every word. So if a sentence had 10 words, we'll raise 10 activities and so on and so forth. So let's do a quick save. I think all that will build. So let's go ahead and build our next guy. Probably, do this one by one, but that's okay. So let's do a counter bolt, and we'll do the same thing. He'll extend the base basic bolt, which needs to come on basic bolt. Implement some methods. I'm going to implement those two methods for sure. What are we going to do from here? So let's do a couple things. I again suggested the best thing to do is do the output fields first. So let's say, what are we going to raise? New fields, and we're going to raise new fields, and they're going to be the word that we care about and the count that we're raising for that word. So what did I mess up here? Didn't call the method dot declare. There we go. I think that'll take care of that. So we're gonna get a word one at a time, and then we're gonna augment and update our existing words. So that said, before we kind of implement our logic there, we probably have to do something like maintaining in this object's memory, maybe a map of words and numbers, integer, if I can spell, Q, and we'll call that counts, and we'll set that equals to a new, maybe a hash map type, string, integer, and we'll just give it a quick constructor, and then of course we just want all those basic Java util stuff. Here we go, Java util. Yep, Java util. Okay, so we got a place to hold on to that stuff. So what do we really need to do when we get a word in? Let's just do the same thing we did before. Let's grab a word, which is going to be the tuple get string. We could do it by the offset, but we know the name. The name that was passed in is called word, and you see we have word here and we have word here. That's okay. We receive words, we emit a word. It could be a whole different thing. It just happens to have the same name. That's not a big deal. Then let's do, again, a pretty simple little implementation here. Let's just say we got an integer count that's based on our counts.get, and the key over there is a word. And then we'll do if the count is if it's null, what do we want to really do? Let's just stand up, count equals to 0, kind of set that, fall out of this, and then either way from there we can just do a count plus plus, so we increment the counter, and then what we can do is actually put the counts, put the word and count back into the. So what we did here, and I didn't fully finish it here, but we got the word that came out of the tuple. We saw if in our private little map of your counts, did we already have something with that word as a key? Either we did or didn't. We got a local count. We set it to 0, if not, either way we'll increment it. So now we've gone to 1 or to 201, whatever the answer is, and we'll go ahead and put it back. Again, we could do something more elaborate or less elaborate. We could do something with a persistent store as well, such as a space and so on. And then just to help a little bit when we look at it in the screen, let's be a little bit painful here, and we'll say count of and then word, the count of word. What's the word? The word equals, and we'll just say plus count plus. Hopefully I didn't make it too noisy there. Okay, so we're just going to output on the screen something, but ultimately we want to emit out those Now we're not going to necessarily emit new values, the word, and the count. And that needs to be a storm tuple. All right, so there we go. What we've implemented now is, got the splitter that breaks them apart, and then the counter is just keeping track in a local map, updating this thing. We're not going to persist it back to HBase or send it to anyone. We're just going to rolling counter, and again, we're not even doing anything with it. We're emitting it, but since we're going to find out we don't wire anyone else to raise it, we kind of lose it. But by doing this, we actually get a nice information message in a little bit in the logs that help us see what are these two values. In addition to this, we're going to put this one, it'll be a little easier to find in those nasty logs. All right, lastly, let's save that. I don't see any compilers. Lastly, let's put together a Java main to put it all together. So we want a random word count topology. Now this one just needs a good old standard, public static void string of main, thank you, main string of args. And so we got a little Java main, great. And here what we need to do is do that topology builder thing we talked about before. So topology builder, yep, that's the one we want. Topology builder equals new topology builder. I don't think we need any arguments on that. So we got this kind of guy to help us get going. As I mentioned earlier, you just kind of walk it. So we want to set a spout, and we'll call it something. So we're going to call it generator. And what is the generator? Well, it's going to be a new random sentence. Yep. And then we have the opportunity here to actually supply what they call a parallelism hint, as you see kind of popping on the screen there. And what does that mean? It tells us it's not a hint, it's what do we want the initial number of instances of this spout to be. I'm going to run this, and I don't want to get lost in the weeds, so we're going to have a single instance of this thing off and running, just one at one time. That can be changed here, it can be changed at runtime, etc. We'll also add to that topology builder, let's set a bolt. We're going to actually set up the splitter bolt, so let's just call it something that makes some sense. Splitter, and it's a new, what do we call that? Counter bolt, a splitter bolt, there it is. Splitter bolt, it doesn't need anything as an argument, and the same thing, let's do a parallelism hint of 1. Now what's a little weird here is, again, we have to wire it up. And I'll go ahead and put the code in, and we want to say for every one of these bolts, let's get information from the generator. So nothing too magical there. So added a spout, called it generator, just have one instance. Added another bolt, call it splitter of that type, let's have one instance, and then let's shuffle grouping, so a string grouping that says telling the generator just to randomly send this. Now randomly, there's just one, so everything is going to come to it. So that's what we did there. And then let's wire up onto that bolt. Let's wire up another bolt, and this is our counter. So let's just call it what it is. It's a counter, and it's a new counter bolt. Counter bolt, yep. Now this one I'm going to have a little fun with it. I'm going to say there's actually, two of those. Why? Because on this one, we actually don't want the shuffle grouping. We actually want fields grouping. Let me get it working here, and then I'll try to explain why we're doing this. So fields grouping, I think we wired up fields grouping. Remind myself of my cheat sheet here. Fields grouping. Okay, we wired up on the thing we're getting it from, so the splitter, and then the fields that we are wanting to field groups on. So a new fields object, fields, yep. And the field that we care about is word. So I just want to get it going first, and then I'll try to explain a little better. So, we got that bolt pretty straightforward, no questions, it sounds like. Second bolt is going to listen to the splitter, but instead of a round robin from this one to these two, we're simply saying make sure, all elements that come out of the previous one for a given word go to one of these two things. So maybe the word the goes to the first instance, the word dog goes to the second, frog goes to the second, and the has to go back to the first. We just want to be consistent. Why? Because we're going to maintain counters, and we don't want two independent counters of a particular word, or we're never getting good answers. All right, so we got the kind of basic setup. We needed to do a few other kind of boilerplate stuff, so I'll just bang that in there. Conf equals new config. This is just letting, whoops, did I mess up? Let's see. This is our chance to wire up where everything is. Now we're going to use, as you're going to find out in a little bit, the Hortonworks data flow, which will have all this configuration set, so we don't have to change much. But we'll do a few values, such as set debug true, so we'll get some of these messages in the log. And we'll also set the number of workers, which we didn't go into great detail talk about. This is just limit all this to one JVM. Just don't have a lot of room to run everything. And then lastly, let's just put it together. Storm submitter dot submit topology with a progress bar. Let's call it something. We'll call it word counter. Word count. What else do we have in there? We need a, comma. We need a configuration object, and then we need a builder. Topology, so create topology from that. Now that's going to scream that we have this big honking opportunity for, here we go, for exceptions, and I'm just going to slap them onto the Java main here, no big deal, to get us up and running. So what do we have? We've got, a properly built Spout. There it is. We have a guy he raises sentences. We have a splitter bolt that takes each sentence and breaks it into words. We'll put some little verbiage to see in our logs. And then from there, we're going to send that to a counter bolt, which is maintained just from a simple map in memory. And this object itself, referenced class level attribute here, and maintaining independent counts on that here, updating them, splashing them to the screen. And then for fun, we'll go ahead and emit those. No one else today is going to consume them, but we're wiring that up should we want to hook up maybe HBase bolt or something to save those. And then lastly, we built a topology that can wire it all together for us. So let's save it all, let's build it all, and then make sure we get it all off and running. And we'll do a little one that finishes down the bottom. I'll do it was at 1548 a moment ago. Let's see where we're at now. We're waiting for the mojo to finish at the bottom here. And I'd expect it to kind of wrap up any second there. Do. All right, maybe I'll pause it while it's compiling to not bore you to death here. And of course, as soon as I hit pause, it actually finished. So there it is, 1609, date 1609, just rebuilt as well. So let's talk a little bit more about what do we do now that we built this jar, and then ultimately how to run that. So we built that code. That's great. If you have trouble from this lab, from watching this video to produce it again, the URL for that GitHub project is right here on the screen. It's just Lester Martin, and then the project Streaming Exploration, and that looks like this right here, Streaming Exploration. Again, if you just drill down into the project solutions and that word count, you'll find that stuff here. You'll find the a POM file you needed, etc., to build that yourself. That's all we did. We built it, we coded it together, we packaged it up. What we'll talk about next is looking at what do we do with this stuff. So I think I have my presentation over there on the other screen. Perfect. So we're back up. So now we want to take that compiled code and run it in a cluster. So Storm is not just a software framework, it's a runtime service that's available to it, that's actively running all the time, that we bring our topologies to and ask him to run, and you expect he can help us with monitoring, pausing, stopping, killing, reparallelizing, etc. We won't go through all those actions. We'll just submit and barely look at the UI to find a running piece of code, but I want to make sure you understand some of the terms and whatever and whatnot. So if you look overall, and now we're switching gears from, again, that compile time view to like a runtime view. What we're really seeing on the screen here is a couple points that I want to make sure with these next slides walk through. This is a cluster technology that has took the mindset of a centralized brain and a set of worker processes out there. So that centralized brain is actually called Nimbus. So Storm Nimbus is the master, and there's an HA solution. They have many backup Nimbuses and those kinds of things. So in case it fails, no worries there. And then the workers in the master worker architecture kind of model are called supervisors. These are we might think of them as machines, supervisor nodes that themselves run, one or more Java processes. We call those workers. But the machines that Nimbus is talking to, the main process that spawns these additional workers up, is called the supervisor process out there. And what this picture is also trying to show is Storm uses a intermediary agent called Zookeeper. It's a very popular kind of framework of frameworks for, especially in the big data space. A lot of systems uses Kafka, uses it, for example. HBase and others use Zookeeper to help the day-to-day running of a large cluster. What we might visualize Zookeeper here. I always feel a little silly when I say this, but if you think of something like a Windows registry that maintains, kind of these paths. Really, what are the paths for? They're there for applications to store often configuration information, so keys and values. So one of the primary use cases that Zookeeper has is a bit of a distributed configuration a store of sorts. So definitely Nimbus is going to use that concept, that feature. Storm is going to use that for the master Nimbus to share details of what the supervisors should be doing and their responsibilities by updating these folders. And those supervisors are going to be listening. They're going to be kind of hanging on to and be alerted of changes to folders. So maybe there's a folder for supervisor number 3, and Nimbus wants that supervisor to take on some new topology work. He'll just make updates in an appropriate folder. Supervisor will notice it and react. So master process Nimbus, the worker processes, conceptually, I know there's a thing called a worker, but the master-slave architecture, architecture, the worker architecture, they're called supervisors, and they can spin up additional processes to run topologies in, etc. So these next slides just kind of walk you through that. So what we're going to do is we're going to take that jar file that we had, and we're going to run some kind of command line argument and say, hey, we're going to connect up to Nimbus, and we're going to say, hey, here's this jar that I built, this Uber jar that I built that has everything I need. Please run it. Please submit this and get it off and running. So he'll take that. And what Nimbus is going to do, Nimbus is very clear about all those workers, all these supervisors that he has. He knows what's currently busy and not busy, what other distribution and load he has already previously determined and spread out. And then he's going to make some calculations and assignments. He's going to not send a message to the supervisors directly. He's going to use Zookeeper as that intermediary agent. He's going to update some configuration, telling them what to do. And it looks like there's a push from Zookeeper down, and that's fair. It's probably more in reality what's happening, but I would say it's conceptually the supervisors are listening for changes in those folders that have additional key value pairs and configuration. So they'll get alerted. Yep, okay, I need to be doing something different. There's additional work for me to do. So what's going to happen is those affected supervisors now that need this jar file, this application, this topology, they'll reach back out to the Nimbus where the topology, when we submitted it, we brought forward that jar. So the Nimbus is hanging on to that. Those individual supervisors will collect those binaries, bring them back locally to themselves, and then as needed, they're going to spawn up workers as defined. It doesn't mean everybody has to do everything. We might have 100 machines here, 10 machines here. We might really only need to affect 1 or 5, or maybe all in of those as well. But they will then spawn off appropriate processes to run things to the end of time. So that takes us to another demo where we'll focus on seeing this run get submitted and run to completion. Okay, now that we have a better understanding of the runtime environment that Storm needs, that we got, again, from either kind of review in the Storm website, concepts, etc., but definitely from those slides we just talked about, let's talk about where we're going to run this thing. So I mentioned I work for a Hadoop distribution vendor company, and I didn't mention the name, and I'm not trying to make this a commercial, but to get me going, I decided I would use a product called Hortonworks Dataflow. And Hortonworks Dataflow actually includes Storm and some other technologies all together, as you see on this screen here. Again, trying not to make this a commercial for Hortonworks, but much more of a Storm conversation. So I wanted to get this up and going. You can definitely go back to Storm, and there are many ways to get Storm running. Feel free to do it your way. The project I have on GitHub is geared toward a particular version of downloading HDF. So I went to the HDF download page, and then I scrolled upwards, and Hortonworks publishes these little sandboxes that you can download off and run. So I pulled the Dataflow 3.0. I did it on VirtualBox, so I've got VirtualBox over here off and running with HDF3, and that spun up an instance and whatnot. So this is all running. I get that running. What do you see from all that? Well, you ultimately, Hortonworks uses a kind of a package tool called Embari. Net, what I'm trying to show is I've got a few needed services. I have that Zookeeper service that we talked about earlier off and running, and I have Storm. I have very little else running. I just want to get a runnable Storm environment. And if you look really close, you'll see some of those elements we talked about earlier, such as the Nimbus process. So we have a Nimbus service. This is all running on a VM with one machine, so it's just what we call a pseudo cluster. One master, obviously no HA setup, and then a single supervisor on the one node that this cluster has. Obviously, for something bigger, even for doing some rigorous testing, you need something more than that. But it's enough to kind of get us started. So we have all those things in place, and what we need to do now is, oops, wrong window. We need to go find our. We did build this thing, I'm pretty sure, right? There it is right there. I think that was the last thing, so I'm going to trust it's in good shape, this long snapshot jar. We need to get it over to the cluster. So let me do a secure copy to that box. So we want to move the Storm word count jar, and we'll put it over there. And we're just doing everything as the user root just to keep it even more fun and less realistic to production. So and I created a little folder over there called Storm Jar. So let's do a secure copy over there. Boom, boom, boom. He's all there. Let's jump over there, do a quick tab, and log into the -v12222 root at. Just logging into that box. And I created a Storm Jars folder. And in fact, there's some RM Storm Kafka just to keep, so clear ls -long. So we have the Storm jar file that we just pushed up. Hopefully just pushed it up. Yes, just a few moments ago. We have that puppy. As I mentioned, what we needed to do, we have to do some kind of submitter process. So without going into all the details, it's all docked on the website there. I'm just going to use Storm's jar command, reference that jar, then I have to reference the fully qualified class name of the topology. I think we called it random word count topology. And if all goes well, which it may, we'll get an echo on the screen here of a ton of jar files as this thing kind of gets started up. Taking a little longer than I was hoping for. Yep, there we go. Kind of blast the class path and those kinds of things. And then there's going to be a little bit more of another maybe 5 to 15 second delay here, as everybody talks to everyone and decides it's valid, looks good, sends the jar file up to Nimbus, and then Nimbus starts his business of associating out to through Zookeeper out to the supervisors. There's only one supervisor who needs to do what, when, where, and why. So it's taken its good sweet time. I think I danced around as long as I could or should. I'm going to attempt to hit a pause, but look there, I think it's coming back. Great, so I'll just let it play through. And what you kind of saw, this magic kind of suggested it uploaded over there to Nimbus, that jar file that we just processed. So we actually have our topology submitted. There are a bunch of other command line tools to see what's running and stop things and reparallelize things, but let's just jump over to the GUI screen here. So as I'm looking at Storm in this Embari tool, they have a reference to the the classic Storm UI. There's actually a kind of revised and Bari view of this as well, but just keep as mainstream project as possible. And I pull up the old Craigslist looking GUI here, kind of boring, but tells us a lot of different things if we really look. And we're going to focus on a couple things. We're going to drill down to the topology section. And if you remember from our code, which should be right over here, when we created the topology, we submitted it, and we said, let's call it word count. So what you're seeing here is there's a topology running called word count. And this is what I meant, that in a real system, that string that you submit, you probably want to put some smarts to this or some naming standards. So when I have 10 or 100 or more, 1,000 of these things, we can kind of figure out who's who and what's what, not just silly words like word count. There's other stuff in here about configuration, about all the supervisors. Again, we only have one supervisor. We're going to just drill into that topology word count. Let me make it a little bigger too so you can hopefully see it. So yep, let's drill into word count. And you're going to see some high-level statistics, again, not trying to cover about how long running and how many resources and so on. So I drill into the topology, and what I expect here, just because I've seen this a few times, the pieces that matter to me the most right now are a list of the spouts and bolts that exist for this environment. So good news, there's our generator, our splitter, and our counter. And just to toggle back, where did those names come from? Because we called them the generator, the splitter, and the counter. No, nothing magical. So those are our names. And in fact, we let it run for a few moments here. We're actually starting to see some details, such as that generator emitted 20 sentences and transferred them and all this good stuff. Took them no time at all, of course. Our splitter, we had one instance of a splitter. It emitted about 140. So for roughly those 20 sentences, it emitted 140 words. Now these are all independently doing snapshots, so they're kind of rolling windows of data, so they're not always going to perfectly sync up, but they should be reasonable. I'll refresh it just to see if those numbers went up a little bit. There we go. The generator, by this point, remember we're doing 3-second delays. Every 3 seconds we emit another one, and we're seeing roughly that the splitter's making whatever that is, 6 times, about 6 sentences, 6 words per sentence, and then the counter is, should these numbers do equal up, they just don't equal up right now because point in time, etc. And we actually have 2 instances of those. You can drill into anything at any time and see about them. Now I'm going to go and cheat and kind of, I'll drill into the generator. The truth is they're all running on one VM, so wherever I go, I'm going to get to the same place. So let's just, for fun, we'll click on the counter. Click in here. Again, more details about windowing and stuff, but mainly what I want to use this for is to kind of drill down and find these independent. We didn't talk about all the terminology here, but the executors, these places that run those instances of the components. And I'm going to click and know that for this environment, I need to play a little game there with the URL and switch it over. What I'm looking at is that independent workers log. What is it doing? Now, most of this is details that make sense to Spark, but if you remember, I put me a little bit of some sysout statements so I could see things like, hey, our random sentence spout emitted a sentence called 7 years ago. Make that a little bigger as well. This was my sysout. Because I had on debug mode, it's going to show some other stuff like, hey, he emitted a sentence. You get a lot of detail if you look really close here. So the generator emitted this sentence here. And there's other ones. If you kind of look, I guess you'd have to look about 3 sentences later. About 3 seconds later, there's another one, Snow White and the 7 Dwarfs, and 7 years ago. Again, if we had a big enough cluster, then I would drill into each one of each components, because they would run in different places, but the logs are commingled. Why? Because we really got one big JVM that's running that everything's within, which is okay, especially for testing, and definitely for what I want to do. I want to see everything together in one screen. What should we look for next? We're looking for things like our splitter. Splitter took 7 years ago, emitted 7 years ago. Those are my sysout print lines, and right next to them is the debug messages, the info messages that we turn on debug wide open to kind of put this stuff. These settings in practice, I wouldn't do these sysout print lines. I would let the fact that at runtime I can toggle how much debugging I want, and it would start out pretty lean, and then maybe if I was trying to get an awareness, I would twiddle that down to be much more verbose in these logs to help me find things. So I got my generator. my spout, sorry, my splitter, and then what I'm really looking for is my counter. And here he is. He's counting. And actually, I probably jumped into it midstream here. We're looking for, hey, I found 22 instances of and, 13 instances of for. And really what would be nice to pick up right about here is pick one in flight. So I'm looking for a word that I could repeat. And for, and, a go, Snow White, and might be a good one. See if I can catch that one in stream. And. There's and 23, and we were looking at and, I thought we were looking at and up here of 22. There we go. If you look really closely, we raised another sentence in here that had the word and in it, and ultimately we got to see the splitter break it apart and do a counter. So we're just showing that all those different components are working. And in fact, if you look kind of close, again, we wrote sysout print lines of that, and even though no one consumes that word and count, there's no one downstream that cares. We, at least because of debugging, have it turned on and see something of value here. So that was mainly what I wanted to show, that we can drill into this thing and get more details. I'm going to go back to the top of Storm UI, find that particular topology. Again, at this point, look at the numbers. We're seeing it rolling well. In all reality, we kick a topology off and we run it forever. I mean, that's what we're talking about here. The command line that I mentioned that we started, we can stop we can kill it. That's what I'm going to do next. But there's other things. That log level we talked about. There's rebalancing. This is that parallelizing as well as revisiting. Maybe I've introduced more machines in the cluster and I want to force it to the system to get another look at how things are laid down. We can pause something. We can actually slow a cluster. We can stop a running topology without stopping it. Just pause it, quiesce it, and then reactivate it. I'm just going to kill it, and gives a little time delay how long you want to wait. We'll let it do 30 seconds. Let everything in the system flush themselves out for the most part. So that's really a simple example of taking that word count topology we had earlier, kicking it up, and seeing it in practice running. And that's really what I wanted to show with this next demo that we just did. I just killed it, and I realized I did want to show one more feature from the GUI there. So I started that topology, submitted that topology up again, and got it off and running. So here I'm in my Storm UI, and I'm going to drill down and find the particular topology we're talking about. So it's been running for about 6 minutes in the background here. And just want to run up some statistics as we talked about, 6 minutes, how many workers, etc. Rolling windows, the last 10 minutes, 3 hours, all time. Again, these are long-running workflows. That's what we're trying to imagine. So we saw these numbers get a little higher, 120 sentences emitted, those kinds of things. The thing I really want to show is this little topology visualization. So I think it's pretty slick, and it's relatively new in the GUI here. And what we're trying to get here, at least at quick glance, is some awareness of what's going on with this topology, some point of reference, some relative information back and forth. So color coding, bolts in blue, spouts in blue, bolts in green, and a couple different things about, the thickness here is really about how many messages. So this one, as we know, the splitter actually sends about 6 to 1. So this is about 6 times thicker than this. So if you really kind of drill into it, you can kind of get some details about compare and contrast. And then some overall, what's this thing taking to do its work. So I'm not sure why our splitter's taken 2 milliseconds, it looks like on average, to burst things apart. But this is an environment, my Mac running VirtualBox, the VirtualBox running the VM's running a Docker instance, the Docker instance is running a full Hadoop cluster. So I'm going to give it all a little slack that it's taken 2 milliseconds to burst that string apart and emit a message out, etc. Again, not the most perfect UI, but definitely something that's relatively new for those of us who've been in Spark for a little while. Have a little fun with it there. So I'll collapse that visualization. I mentioned that there was a lot of command line operations. I'm just going to show you a couple of them here. Storm list is the same way of seeing those same running topologies. We should only see one, the word count, which is what we have often running. And while I'm giving the system a little bit of slack, I'm not so sure what's taking it so long to tell me a list of running topologies. So maybe I'll give up on that in just a second here. Not sure what's going on. Here, I'll pause it. I'm not sure why that's happening. And like every other time I paused it, as soon as I did that, it actually came back. So it ran, as it says here, I got topology word count active. been up at 513 seconds and so on. So, we can use the GUI to view things. We can actually use the command, the GUI or the command line. We'll just go ahead and use the command line to kill that word count. I'm going to leave off those wait seconds. We'll just force a kill immediately. Hopefully that'll kill it off. Well, we'll trust that it's going to kill it off. I'll jump into the presentation as well. Come back to it if there's a problem. Command from this slide. There we go. All right, so really only gave you a taste. We're about an hour into it. Again, I'm doing this really to prepare for a user group meeting. I wanted to get it down, check the timings, and ultimately try to maybe put a little conference submission together for this. So the reality is, it's a big framework. It's a mature framework. It's been a while. There's a lot to Storm that I haven't talked about, explained. I'll just hit on a few more of the points here, not explain them in great detail, but just whet your appetite. And then again, we'll finish up with a final demo of seeing something a little more exhaustive than the simple word count, something a little more integral with other technologies as well. So some additional features. One for sure that's going to be helpful, and I'll do it in the demo, is running. It's nice that we can run in a real cluster, but we have to move the jar, submit the jar, and those kinds of things. We don't really have a great opportunity to debug. We can look in logs and so on and so forth. It'd be better to run it out of your IDE. So we have a notion of a local cluster as opposed to the full-on distributed cluster that emulates it, does it all on the same VM, uses threads for workers, that kind of stuff. And as the screen's kind of showing you here, the reality is, you can be very low tech. You can just kind of hard code you something like this. There's a, local cluster has a submit topology just like the Storm submitter does, takes the same arguments and so on. And you can write your code or comment it out, uncomment it out. I think in the project I have, that's what I'm doing. But, use a dependency injection to kind of control which one of these topology submitters that you want to do. Do this, run it out of your IDE. As you'll see in my demo in a bit, you can actually put breakpoints and so on and so forth as well to slow things down, to see how things are working, interrogate data, all that normal stuff that we'd probably want to do in normal software development. A big thing that, again, not time to really get into it here, but just to make sure you're aware of it, is one of the definitely mature elements of Storm is this notion of a reliable operations, reliable processing. So what's happening as we send these data through the framework, through the topology, something could blow up. In this situation, maybe the very last leg, or maybe a leg in the middle, something blew up, and this tuple that left the spout never really made it all the way through. So either it traverses all the way through, or additional data gets created, manufactured, augmented, whatever. It doesn't matter. It's child data. It relates to it, and the framework can be made aware of that. Remember that we saw some acts and messages. We saw some fails and those kinds of things. So there are hooks for us to leverage to say, hey, I want to enforce this reliable operations. And they're again, more than we have time to talk about, but it's available. We anchor things as we go along, and that tells the framework kind of, hey, we're supporting this notion of a reliable operation. And they create this concept called a tuple tree. Meaning, as we have raised one event, just like we saw earlier, our spout raised the sentence actually got broken to 6 or so words, and each word got sent further down and got created into word counts. All of those derivative data that came off that one sentence are all part of that tuple tree, and we need to make sure that every event, every tuple that leaves the spout, if we're enabling reliable processing, we need to make sure it finishes all the way through without exception, without blow up. As long as, we have opportunities to shell out and say, no more, we don't really care beyond this point. But in general, all the way through, and not just complete, but complete in a timely fashion. You might have noticed when I killed the topology from the GUI, there was this notion of, hey, how many seconds do you want to wait? And pick the default value of 30. Generally speaking, we're talking about the system default is set to 30. We can change that number of seconds. And if not only do we have to finish well, we have to finish within that time window, or we abandon and say, hey, you know what, it's time to replay that tuple from the spout. It didn't make it. So we're acting as we go. We have the opportunity to mark things failures, etc. And if at any point something blew up, something raised a failure, or the timeout triggered before we're all finished, the framework's going to basically go back and ask that spout. It's going to notify that spout of an identifier that he coupled. We did not do this. Because we didn't raise an identifier on the spout, we can't have reliable operation. So the prerequisite is the Spout must raise an identifier. For things like Kafka, this is easy because Kafka has partitions. Partitions have offset, so we're kind of carrying that information under the covers in those tuples. So if anything doesn't make it, the replay comes back. The system hands back basically that offset. The Spout's then able to go back to the event store, the message store, and pull that event out of Kafka again and force it back to the system. If we wrote our own Spout, that could be difficult. Depends what we have and what we're doing. But the framework does support this notion of reliable operations. Very powerful. And there's a slew of other stuff. I just have a couple bullets here, then I'll stop and show that last demo and wrap this video up for the day. I know it's getting kind of long. I was shooting for an hour. I think I'm a little past that now. So we did topology submissions via Java. There are other things. There's this notion of Flux, a little bit more of a JSON description of what we're doing. There is a relatively new feature called Storm SQL. I'm still trying to wrap my head around, is that cool or not cool, but describing topologies via SQL. So if there's interest there, go to storm.apache.org. There's plenty of information there, or Google around for that. We focus today on Java because that's really the first-class integration into Storm as a Bolt and Spout and topology builder. But Storm will allow us to write in any language. It's just going to, under the covers, spawn those processes up in shell, send information to those processes via standard out, wrap them in JSON, that kind of stuff. So we can do polyglot development. We can use other programming languages. I would say try to stick with Java and realize maybe there's some code you have that lives in another language, and maybe implement just one of those elements, one of those bolts, etc. If you're just, my opinion, if you're just going to do all Python, for example, maybe Storm's not the right answer. But just this is Lester's humble opinion, maybe not the right answer. Java seems to be the primary first-class mechanism. Other frameworks, this notion of event-level processing is almost unique to Storm. Most of the other frameworks, such as Spark Streaming, support a concept called micro-batching. I think someone coined it well. I think he works at Hortonworks. Said, Storm is a stream framework, a stream-based processing framework that can do micro batches, that can do batches instead of events levels. And then frameworks such as Spark Streaming is a batch framework. Spark is a batch framework that can try to do streaming. So I'm not suggesting Spark Streaming is bad. It's good, interesting stuff. Go for it. No complaints there. But it only does micro batching by its architectural tenets. We could do that as well in Storm through a subcategory here called Trident. It's all part of the core Storm project as well. There's not any time to get into that. And in fact, that API for Trident looks a lot like the API for Spark Streaming. So if you've done some exercises there, you might look at Trident first. It might be easier for you to get your head around it and then work backwards from Trident down to Storm. I'd start with Storm and work up for most of us, but if you have that background, it might make a little more sense. Plenty of fault tolerance. We talked about that. The system needs to be able to handle all kinds of failures all over the place. That's what the system's about. Including and additional things like deployment isolations. Maybe you have 50 machines or 10 machines devoted to this cluster, but maybe there's these 2 machines that you want to say, only topologies 1, 2, and 3 can live on those particular machines. Lots of maturity and sophistication in this framework to allow things like that. And then, of course, and what I'll kind of focus on a little bit in this last demo before we wrap it up, is there's a lot of inherent bundled with Storm proper, integration hooks from Spouts and bolts. So, like it says, messaging platforms, Kafka and others, these exist already. You don't have to write the code. You just instantiate it, as you'll see on my example next here, wire it up the necessary configurations and let it off and run. But it goes the other side too. We have bolts to write to databases, to write to search engines, to read from search engines, to read and write anywhere. And again, just like Kafka, we have a Spout. We definitely have a Kafka bolt. We put things back, write things into HDFS and other places. So much more and then more stuff than that, but just want to throw a few things out there. What we'll end up doing is try to finish the rest of this video out with a comprehensive demonstration with a few other technologies. So here we are with the final example of the day, of this video here, I guess, the day. And as promised, this is going to be a little bit more complicated than the word count one that we showed a little earlier. But, again, not overly complicated. The whole point here is really to bring in some other technologies and show you that Kafka already has some inherent functionality to adapt to other things. So quick overview of this example we're going to build here. We have a Kafka topic that exists over here on the left-hand side. And what's going to be thrown in here by a little simulator we have is a bunch of log messages, info, warnings, errors, those kinds of things. And we're going to collect them, assuming we're collecting them from a server farm. We want to have a storm topology that pulls in all those events. So I'll have a Kafka spout. We'll actually not write a spout. We'll configure up a spout that pulls from Kafka and then emits that information down into our workflow, our topology. Just the way I implemented it, it's kind of a string. The whole message is a string, so I'm going to build a parsing. I'm going to handwrite a parser bolt that helps us break that into pieces, and then we'll just pass that along. We'll build our filter, kind of a homegrown bolt here, filter that's going to do basically this third bullet here. We're going to look for warnings and errors, and if we find warnings and errors, we'll carry those forward. We'll emit those out as a stream. Everything else we'll just throw it to the bit bucket and move on. And then of those warnings and errors, we're going to wire up basically an H-base bolt. We're not going to build one. We're going to configure one to find those values and write them to a popular NoSQL system called H-base. And just at the same time, we're having a different subscriber to that stream, a Kafka bolt this time, that takes those special messages that we care about, those log messages, and we'll write them to another topic in Kafka. So hopefully it'll be a little bit more interesting than the simple word count. So I'm going to jump over here, and I guess let's look at the topics first just to see it. I've got a little generator right over here, a little script that I'm going to kick off in a little bit, a little Python script, but just to generate messages. But what it's going to do, it's going to write messages that look a lot like this. This is just the output of the table here. On the right here, I'm just saying, hey, go everything in Kafka, grab everything from logs, and let me just tail basically the message. Let me consume those messages. Just as much right below it, I'm tailing another topic called bolt. Terrible name, but it's the one that the bolt's going to write to. And this is the one that's going to receive just the warnings and errors. So they should look very similar. If you look really close, you'll notice I lost the precision of the timestamps and the dates. That's just, you'll see that in the topology. I was just trying to make it simpler and have less code. We'll see that in action. And then over here in HBase land, what I kind of stood up already was the fact that we have this notion of a table already created called incident that we're going to store these in. HBase is not like a relational system, so it doesn't tell you a lot of details about columns and whatnot. What we really have is, let's see if I can show it to you. It might be better to do it this way. Let's say get incident by the row key called 9.9.9.9. So this is one row in there. Just 3 rows. Maybe if I said scan, it might make a little more sense there. Scan is like select all. HBase is a kind of a key value store, a very interesting model, but we still kind of think about like primary keys. We call them row keys here. So what we're storing here is just the example here, warning message, warning type of message. It was called a message, and then we're having an independent counter. Because back in the requirements here, let me pull it back on screen, see if I can tell you here. We want to keep the 10 most recent messages from each server, but we want to keep a running total of all the messages. So if we get 1,000 messages, we want to be able to recall the last 10 messages, but we want to know there were 1,000 messages. And HBase lets us do that, lets us maintain versioning on these elements. So what we're going to see over and over, and I'll maybe just, I think I have it in my history up here, 999, let's here to go. Let's put an error message, and let's call that, where's that in there? The details, it's an error message. Again, I get it if you're not totally familiar with HBase that this is probably not making perfect sense, and that's okay. I just want to show you that we're going to store some data here. Now if I ran that same get earlier on the one row, what we're going to see here is, oops, I didn't tell it. I wanted some versions. Versions equals 10. Let's get up to 10 versions. Oh, I guess I messed that up, didn't I? What did I do wrong with there? Oh, column event. For the column, basically the column family, called event. Let's see, 10 versions. How about that? Okay, for the same particular field with 999, we're actually showing, if you look really close, there's 2 different versions of everything. There's 2 types, there's 2 details, and in fact there's 2 totals, 1 and 2. In practice, this thing will can go deeper and deeper, but again, probably the easiest thing to show is, let's do a count on incident. We have only 1 record in there, so 1 row key. So okay, so as we see more warnings and errors, we expect this to go up by that same kind of number. All right, so that's a little bit of a backdrop. Maybe we'll jump in and look at the code. All right, the code. We have a topology like before. And if we, let's make this a little easier to see. Click on, double click. There we go. So in that topology, what are we going to do? We want to do like we did before, where we, somewhere in here, we got here we go, line 27. We want to get a topology builder. And then line 38 down here is what we want to do now. We want to set a spout. So we're going to set a spout. We'll call it the log spout, but what we did before is we instantiated a class that we created. What we want to do here is, let's use an existing class. So what is Spout? Spout is a Kafka spout. Okay, great. Knows how to connect to Kafka, etc. What does a Kafka spout need to be constructed? It needs a spout config. And what is a spout config really doing? It's really saying, hey, where am I going, host? Where's Zookeeper in this case? Since Kafka uses Zookeeper to help it out. Help me find this Kafka cluster and then tell me the topic, the message queue that I'm looking for. And then for the most part, this says just go get everything in there. So we just, wired up in a few lines of code here, an object that knows how to talk to Kafka, and we appropriately pointed to the right cluster, Kafka cluster, and the right topic that we want to pull from. So there's our set spout. We only have, and then I mentioned we're probably going to do some kind of parser of that, so I decided to call that a message tokenizer of sorts, so I'm going to set bolt, this new thing, the message tokenizer. It's a message tokenizer bolt. We'll look at that class next, and we're going to wire it up to pull from that Kafka spout, log spout. So let's look at the message tokenizer. Nothing too sophisticated in here. In fact, he is just being handed, we're getting from the tuple, what did the other one raise? We didn't have an opportunity to really kind of describe a field. So earlier we used like get string by field name. We can do a get string by zero-based numbering system here. So basically the first element, the only thing in there. So get string, the first thing that's in there. And then I'm just going to split that by tabs, because if you remember when we looked at the logs, they are tab separated, the different elements. Great. So what do I have? I have a little array of strings that I've decided I only want a few of the elements, the IP address, the message type, and the message details, information, warning, error, those kinds of things. Got some output, so if we want to look at that in our, make it kind of obvious and see it in the console, great. A little extra noise, of course. And then we just want to raise that back up. So we're going to raise a 3 tuple with the IP address, the message type, and the message details. And you see that kind of echoed again in our declare our output fields, where we actually have to say what are the names of those fields. So now we've taken the message from Kafka, we've broken it into discrete fields that we care about, throw away some things that we don't, and we're off and running. At this point, we need to do our real smarts. We're really looking for the warnings and the errors. So basically, we're going to set another bolt up that's listening to the message tokenizer's output. And what is that? It's called a message filter bolt. This guy is the one that's looking for warnings and errors. So got a little array up there. What am I doing? I'm getting from the tuple. I'm just simply grabbing the message type to get started with, and then I'm just doing a simple if statement. Hey, if that message type is in these list of I care about message types, then obviously we don't want to do something. What do we want to do? Well, really, all we want to do is emit that value. We're going to emit those values back out to the next guy. So we're going to emit. We'll go ahead and grab the IP address and resurface it. We already grabbed the message type, so we'll package that and the message details. So we're just kind of raising those things: IP address, message type, details. And interestingly enough, we're going to help because we have some coupling downstream. We're just saying how many events were there of that. So we invented one more field. So we had a 3 tuple coming in. We're creating a 4 tuple on the way out. And I'll explain a little more about why we hard-coded a 1 there in a second. It kind of tells you here. We're going to use it when we configure an HBase bolt to say how much are we incrementing. So how many records does this represent? It represents 1. So we'll be able to increment it. The rest in here is just a bunch of if and else to put a bunch of says out print lines that, again, maybe not the cleanest thing to do, but when we're debugging this early on, it might be somewhat useful to get us going. So back to our pretty picture, we've got the bolt, we've got a kind of tokenizer or parser, we have the filter, and now we're down at the very end of our topology. And to be honest, really, the only logic we wrote was maybe in this tokenizer and this filter. And we could have done a better job of having interesting, more declarative objects in the topic than a string with tabs, but that's what I chose to do. So we're living with it. All right, so once we have that, what we're probably going to imagine is the filter bolt here. We're going to probably want to configure something to listen to this. So I'll jump to the bottom. It's down here. Set bolt. I have a builder set bolt. We'll call it an HBase bolt. We'll talk about what it is in a second. He's the one that's listening. Again, up here to the message filter defined on row 44. A lot of this is just to wire it up. We looked at HBase a minute ago, and what this is saying is we want to construct an HBase bolt. We want to know the table we're going to go to, and then we want some kind of helper class, a mapper class that helps us figure out how to take the data we're getting and how to map it up to stuff. So what did we get? We had IP address, we had type, we had details, and we had that total. Those are the four tuple field names that we had coming out of the message filter. And this is just how we're going to wire it up. Again, if you know a little bit about HBase, you can probably read from this, and if not, I'll just kind of run you through it 100 miles an hour. This is the row key itself. The IP address will be the row key, the primary key. We're going to use the column family called event. That's just a kind of a higher order concept. And then the fields we really care about are event type and event details. So that's how this and this go together. So we're just grabbing, we're saying carry forward the type and the details that were passed from the previous bolt. And then we also want a special field called a counter. We kind of showed that with the increment earlier. Well, let's also increment by that total. This is that hard-coded number 1. So this will let us take that record and write it off to HBase and move on. So again, really didn't write any code to do any of that. We had to wire up basically, the HBase bolt and use it. It needed a little bit of a mapper, and we're off and running. Lastly, and I had some of this kind of scattershot because I actually added the Rust right to Kafka at the tail end. So let me just kind of zip forward toward the bottom. And ultimately, I wanted to have a bolt called a Kafka bolt that I put this message back in to the topic. And I wanted just to keep the same thing I had alive earlier, which was a simple string that had tab fields in it. So what I really decided to do is let me go ahead and listening to the filter as well. This is the same place the HBase bolt listened to. Let me have the flip of the tokenizer or the bolt earlier to have a reassembler bolt. So this is just kind of the reverse of what we talked about earlier. He's taking those different fields and just slapping them together with a string buffer, IP address tab, type tab, details. So it's building something like that. So it's just building a simple record out there. A record that includes the IP address, but if you notice we actually say let's raise IP address and then this delimited record, which includes IP address. Why? Well, why? Because Kafka gives us that opportunity to say key. Kafka is a multi-partitioned message queue, and we often would use a key to say, hey, add this, and the key drives it to one of those partitions. For our small, simple example, it's not all that important, but it's something that we would do in practice. So we broke this apart. We reassembled the broken apart fields down to something. So that's how we got here. And then we want to wire our Kafka bolt to say, give me that, and do something with it. Kind of like HBase. If we work backwards, we have to have a few things. We have a Kafka bolt. We need some properties. Where is it? Where's the cluster at? How many times am I going to wait for things to go well? What are my, serializers, that kind of stuff. But ultimately, I'm going to say this right here on 86 with the topic called Bolt. That's the one we're listening to over there. And then, hey, what's that again? That kind of mapper class to help us backtrack this and get it in there. And here, we're going to just use a kind of pre-built one, the file and field name base tuple to Kafka mapper. And there's that IP address I mentioned. There's a concept of like a key, but the real message is that delivered record. I know that was a lot. This stuff is in that GitHub project that we mentioned earlier. You're definitely welcome to take a harder look at it there, etc. But at this point, we probably want to see it run. So last thing I would say, compared to what we did earlier, and I left it kind of commented out. Earlier we used the full Storm submitter to submit the topology. Here we're going to use a local cluster so I can run it right here in the IDE. So I've already built this in the background, so I'm going to kick it off and run it. Run analyzer. Let's get this started. I'm going to maximize this window, and it's going to burst a bunch of stuff, but I think what's going to be more interesting is for me to flip over to workspace 1 and hopefully catch some of this stuff in action. What we're looking for is, well, actually, we probably need to run our simulator. So let me go ahead and tell you, we actually had some data that we drained, so let's do a count on incidents. So we have 14 records that we found in. This is the raw log messages that come in. These are the replays of just the bads, and these are the HBase versions of just the bad. So let's do ourselves a favor. Let's kick off our generator with a whole one transaction, one new event per second, just to keep it manageable and readable. And if I put this up, we should see about every few info. We're waiting for something like a warning or error message to bump this down here. So debug, info, there it is, error. So you notice once the error triggered here, it triggered one down here. Why? Because the whole message queue, the whole topology is looking for those so we can write just the bad ones back off. And if that's true, we've seen maybe 3 or 4 over here. So if we did another count over here, we should see it incremented there. It's up by 5 now, up to 19. So nothing too magical. Let me go ahead and pause this thing and we can talk about that if it really mattered. But so we saw it in action. We got the topology running over here, and we're running right out of the IDE. And I didn't do a breakpoint and those kinds of things, so we could have. It's actually still running. I could kick it off again and connect to it. I'll just stop it. Again, you could do your normal stuff that you do in your IDE. You could put breakpoints and trigger things and that kind of thing. But this code is, at its heart, really just trying to show you that we can, read easily from Kafka, easily write back to Kafka, easily write to something like an HBase or other database. So lots of good integrations pre-built in. And at the end of the day, we were able to get this bit of functionality working the way we had hoped for. Well, that wraps it up. I hope it was a fruitful amount of time spent today listening to this. Again, the information is available to you on Twitter. Twitter, on GitHub out there. There's some additional information about me. Should that be any interest, anyone want to reach out to me, definitely through. I'll put a blog post about this meeting and my first presentation at a user group with this deck as well. It was a pleasure. Hope you got something from it. Thank you very, very much.